Hi everyone, this is my Physics 2211 Lab 4 report video. Here is a brief overview of what I'll be covering in this video. I'll start with the introduction, then the fundamental principles, along with the procedures and experiment and analysis from Tracker. I will conclude with the sources of error and the discussion questions. Moving on to the introduction, the purpose of this lab was to examine the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring and create a computational model based on the momentum principle and the energy principle. Tracker was used to analyze the video, and GlowScript was used to construct the computational model. A preview of my results is that the change in total energy is 0, and the observed versus predicted model deviated only slightly. Starting with our first fundamental principle, we used a computational model based on the momentum principle because it states that the net external force acting on a system causes a change in its momentum over time such that the net force is equal to delta P over delta T. Here we have the velocity update formula and the position update formula. These allow us to calculate the velocities and positions of the spring over time based on the forces acting on them. They are also derived from the momentum principle, which we discussed previously. Here we have the equations for kinetic energy, gravitational potential energy, and spring potential energy. These allow us to compute the system energies and is used in the GlowScript code. They are also derived from the momentum principle. Now we have the energy principle, which connects the changes in a system's total energy to work and energy transfers with the surroundings and is given by delta E of the system is equal to W of the surroundings plus Q. Here, W is work done on the system by external forces, and Q is energy transferred as heat into the system. For this lab, it can also be written as delta E is equal to delta K plus delta U of the spring plus delta U gravity. For procedures and experiment, I uploaded the spring mass video to Tracker to extract the position data. I collected data from Tracker to create a spreadsheet with X and Y values. I then edited the starter code accordingly using the pre-lecture videos. Finally, I ran the program to attain output by inputting the .csv file given by Tracker. For this lab, the system includes the mass, the spring, and the earth. And the surroundings is everything else, but in this case, it's nothing. Now on to analysis from the Tracker. Here, from the Tracker dataset, we have the initial position is negative 0.11, negative 0.6430, which is circled in red. Now for the computational model. The initial conditions are highlighted in orange. Ball.m is equal to 0.402 from the pre-lecture video, and the initial conditions were set from Tracker data points from the previous slide. So ball.position is equal to negative 0.11, negative 0.6430, and the velocity of the ball is 0. Continuing with the computational model, highlighted in orange is the code that I edited. So from the pre-lecture videos, we have K of S is equal to 6.83, L naught is equal to 0.123, L is equal to ball dot position minus spring dot position, L hat is equal to L divided by the magnitude of L, and S is equal to magnitude of L minus L naught. The last 4 lines are all given by equations from the fundamental principles that we discussed earlier in the video. Again, in orange is the code that I made changes to. So from the pre-lecture videos, we have F of gravity is equal to 0, negative mg, 0. F of the spring is equal to negative k times S times L hat. Ball dot velocity and ball dot position are computed using the velocity update and position update formulas. L, L hat, and S are all calculated from the previous slide, and the last 8 lines were computed to calculate the energy changes. Now we have our results, the observed versus the computational model. Here you can see screenshots of output from running the program and inputting the .csv file for the X position and the Y position. Noting some similarities and differences from the results, in the X position versus time graph, you can see there are only some slight deviations between the model and the experiment. Again, the model is in blue and the experiment is in red. In the Y position versus time graph, you can see there are more deviations between the model and experiment, especially as time went on in the end, and this is likely due to human error. Some possible sources of error include tracking errors. For example, misidentifying the center of mass. Another source of error could come from errors in calculations, such as inaccurate code. Concluding with the discussion questions, for your model system, is the energy principle satisfied? The answer to this question is that yes, the energy principle is satisfied because delta E is always equal to 0, and you can see that in the graph. The orange line here displays delta E. This question wants us to estimate the period of oscillation. I calculated the period of oscillation by using values from Tracker over 3 oscillations. For X, t is equal to 1.614 seconds, and for y, t is equal to 1.488 seconds. So there are some slight discrepancies between t, and this could be caused by sources of error mentioned previously. Thank you for watching this video.